This video is for Tuesday, August 9th, Math 1325, and we're going to be working on section 6.6 and 7.1 today. So let's do this. 6.6, 7.1 today. Tomorrow we finish up the weekly homework with 7.2 and 7.3. Then you got Thursday and Friday for the review that covers these 6 sections. Next week we'll do 7.4 and 7.5 on Monday. And then we'll do probably half the review on Tuesday. There's 30 questions, so half the review on Tuesday and the other half on Wednesday. I'll go over this review just because we're not learning new homework on Tuesday or Wednesday of that week. And then you get Thursday and or Friday, not and or, but Thursday or Friday next week to complete the final exam. So that part's typical of any other week. Okay, so 6.6, slight extension of what we learned in the previous section. So find dy for the given values of x and delta x. Y equals 3x to the fifth minus 5x. X is negative 3 and delta x is 0.1. Round to the nearest tenth. Oops, okay, so y equals 3x to the fifth minus 5x. And then they give me a value, x equals negative 3 and 0.1. X equals negative 3. And then you'll see what this means in a second. Delta x is 0.1. So if you take a derivative of original function, y prime, remember that has a synonym of dy over dx. Derivative of y with respect to x. And this is a polynomial, so we just use the power rule. 5 times 3 is 15. X to the 5 minus 1 is 4. 5x is linear, so the derivative of that is just negative 5. This is what we did previously, and then what was new was that there was x's and y's at the same time. And if you're thinking of literally doing the derivative of y with the implicit differentiation, that's linear, 1y, so the derivative of that is 1, but then remember, if you do y, you have to have a dy over dx attached to it. So in essence, that's been happening the whole time. They just told you to write it this way. So what if I multiply both sides by dx? We never did this before. Then you get an expression for dy. dy equals 15 x to the fourth minus 5 times dx. And this is an approximation of that. So I could plug that in for dx. And this also lets you know that the variable of interest is x. And then I can plug negative 3 in for x. And the directions said find dy, not dy over dx, but just dy, and round to the nearest tenth, I think it said. See, dy equals blank, round to the nearest tenth. And they're building up to what we're going to be doing in section 7.1 is why they're doing this here. So 15 times negative 3 to the fourth minus 5, and then we could even put 0.1 in for dx. Negative 3 to the fourth is negative 3 times negative 3 times negative 3 times negative 3. That's 81. So 15 times 81 minus 5 times 0.1. So it came out to exactly 121. dy is 121. So you just take your dx that's under dy and move it to the other side of the equation, and then they even give you a value to plug in for it. And this is this delta x, that's a way to say the change in x. X is changing slightly as you move across a function by a 0.1 distance. And then y would be changing at a rate of 121 when that happens. Every time x changes by 0.1, y is changing by 121. Because remember how derivative is the slope of a tangent line, so it's like the change in slope. Okay, so similar problem. I got a polynomial, find dy, given x equals 5, delta x is negative 0.2. So the original function y equals x to the 4th minus 9x squared plus 3, given that x equals 5, delta x equals negative 0.2. So dy over dx, that's the derivative of y. And then the derivative of x to the 4th is 4x to the 3rd. The next derivative is negative 18x, and the derivative of 3 is nothing. Multiply both sides by dx. And then we can plug in 5 for any x's. And we plug in negative 0.2 for dx. 4 times 5 cubed minus 18 times 5 times negative 0.2. 5 cubed is 125. Times 4 would be 500. 18 times 5 is 90. 500 minus 90 is 410 times negative 0.2. So negative 82. Anytime x is changing by negative 0.2, like moving to the left 0.2 units, the y goes down 8.2. That's the rate of change for y. Negative, did I say 8.2 or 82? It was supposed to be 82. I don't know where I got 8.2 from. Didn't seem right. Okay, so negative 82. Not 8.2. Okay, square root. Y equals square root of 4x plus 3. Same kind of directions. X is 1 and delta x is negative 0.01. Y equals square root 4x plus 3, 1 and negative 0.01. X equals 1, delta x is negative 0.01. So I would rewrite the original problem as 4x plus 3 to the 1/2 power. The derivative of that is 1/2. Then you rewrite the base. Decrease the exponent by 1, so negative 1/2. And then chain rule, the derivative of the inside, that's linear, so the derivative of that's just the 4, the slope of it. And then this 4 could cancel this 2, leaving 2. And then I can write dy over dx. It's the same thing as y prime. There's a 2 in the numerator. This 2 right here. And then this negative 1/2 could go to the bottom. And I can either write it as a positive 1/2 or put it back as a square root. And then I'm going to multiply both sides by dx. So that we have dy. And again, you could have 2 over the square root of 4x plus 3 dx. So this dx goes in for negative 0.1, goes in for that, and then stick 1 in for that x down there in the radical. So you get 2 over 4 times 1 is 4, plus 3 is the square root of 7. And then we plug in negative 0.01 for dx. And this is where now rounded, all the answers have come out evenly up to this point, but now we're going to round to whatever they say. Round to the nearest thousandth, tenths, hundredths, thousandths. That's 3 decimal places. So 2 divided by the square root of 7, and then times 0.01 negative. Thousandth is 3 decimals. There's a 5 after that. So you got to add 1 to the 7 and make it negative 0.008. .008, maybe the younger brother of James Bond, 007. Okay, so the first 3 problems, same kind of directions, just the derivative's different every time. The next couple of problems is using this idea to approximate things. This was very useful a couple hundred years ago when they didn't have calculators. And it's the basis for how calculators approximate answers for us. So we want to approximate the square root of 73. Okay, so what you want to do is get the closest square root to this that comes out evenly. So we have a choice between square root of 64, which is 8, or the square root of 81, which is 9. 64 is 9 away from 73. 81 is only 8 away, so we should go to the closer one. And I'm going to do the square root of 81 is 9. The distance from the value I'm going to use and my actual answer, this is the delta x. So I'm 8 units away. And then x is going to be the value that you're actually going to use, which is 81. That's the one that comes out exactly. So it's like I have in the first 3 problems that if I was told that the original problem was just the square root of x. Now I'm using x of 81, but just in general, square root of x. So the derivative of that with respect to x, if you think of this as x to the 1/2 power, is 1/2 x to the negative 1/2 times the derivative of the base, which is just 1. So that's 1 over 2, and you can put x to the 1/2 in the denominator or change it to a square root. And then multiply both sides by dx. So here's an expression for dy. This is how y is changing. It's 1/2 square root of x times dx. So 1/2 square root of 81, which we know exactly what that is, and then times this 8 since we're 8 away. And the 8 could go into the 2 4 times. So 4 over the square root of 81 is 9. 4 divided by 9 is 0.4444. Okay, so this is how y is changing, and then what you do is this is the format. It's the derivative of x plus the change, how far x is away. So what we just found was, maybe I'm writing that wrong, the derivative of x, 81, 73, no, maybe it's not the derivative, 73.444. So 9, square root of 81 is 9, although it should be, since we're 8 above, maybe I did that backwards. 99 minus 0.444 repeating. Let's see how far they want it rounded. 4 decimal places, okay. So 4 divided by 9 is all 4s. 4 divided by 9 is all 4s. So if we did the square root of 81, that would be 9, but that's too high. We have square root of 73. So we have to take away this approximation part. 9 minus 0.4444, 8.5556 is what my approximation is saying. 8.5556. Now, in today's world, we do have calculators, so this would have been a whole lot easier if I would have just done square root of 73 in a calculator. But see how close that answer is? 8.544. 0 is what the calculator is saying. 8.5440. It was correct to the 10th and just off a little bit after that. So it gives you a quick way to, not a quick way, but it gives you an alternate way to, let me put plus or minus here. It gives you an alternate way to get a square root if you didn't have a calculator. Now, I had one and I was able to get this is a more accurate answer, this one from the calculator, because it's doing more decimal places than we are. But this is how they approximated them back in the day. So what is the value found using the differential? Okay, that's what I got. 8.5556. And then the calculator said it was 8.5440. What's the absolute value of the difference? So in case yours might be higher or lower than their answer, but 8.5556 minus 8.5440. So if you do this and get a negative, just ignore the negative. That's what they mean by absolute value. 0.0116. That's how far off the approximation is. Okay, so that's it. So similar deal here, exactly the same directions as the different square root. Now we have square root of 0.50. Square root of 0.50. The closest square root that comes out exactly is square root of 0.49, because we know the square root of 49 is 7. So the square root of 0.49 is 0.7 exactly. This is the exact answer. So I'm going to use 0.49, and then how far away are my two from each other? 0.50 is my number, and how far away am I from the closest one? Remember last time we were 8 away. 0.50 minus 0.49 is only 0.01 away. That's your delta x. And then you want to use the 0.49 that comes out exactly. We already did the derivative, so we don't have to do it again. F prime of x, or if you want to write y prime. But what we want to write is dy over dx. For a square root function, that was 1 over 2 square root of x. We would normally have to find that, but we did it on this problem. It was right here. Same rule. It was square root of x. The format's square root of x. So square root of x, x to the 1/2, take the derivative. Once you've done it once and you have another problem soon after, you'll probably remember what you had for your answer there. 1 over 2 square root of x. And you put the square root of x, you put the exact value for that. So that one will come out evenly. The square root of x is 0.7. The square root of 0.49. And then you multiply by this, 0.01. So 2 times 0.7 is 1.4, and then we need to do 1 divided by 1.4, and then multiply by 0.001. 1 divided by 1.4 times 0.01. So our approximation is, how many decimals? 4 again? 4 decimals, okay, and this says 4 decimals, okay. So 0071, 0071, and since we're doing, see this is where it's plus or minus right here. When I did this problem, I went to the higher one up because that was closer. I went to the higher exact one, so then this answer's too big, so I have to take that and subtract what we got from our calculation to go back to the 73 level. This time it was opposite. I went from a larger number down to a smaller number, so now this answer is too small. So now we need to take that exact answer and add this calculation we got, and that'll get us back up to the 50 level. So this is saying our approximation is 0.7071 if you add those two decimals together. The square root of 0.49 is 0.7. The square root of 0.50 would be a little larger than that, so this makes sense, 7071. Where the calculator for it, we got to figure that out. If we just did the square root of 0.50, the calculator says 7071. See how that's more accurate than the last problem? So if you can, the closer you can get to it, the better your approximation is. Last time I had a huge difference in how far I was away. I was 8 units away. That's quite a long ways away. So the approximation was still pretty good, but it was only good to the first decimal place. Now that I'm only 0.01 away, that's really close. And then to 4 decimals, both answers were the same. So if I subtract this and do the absolute value, it's literally 0. So that means there's no rounding error out to 4 decimal places. What if we do a log of this? Natural log of 1.04. Natural log of 1.04. The closest one that comes out exactly to this is natural log of 1. Any log of 1 equals 0. Because log graphs go through the coordinate 1, 0. So natural log of 1 is 0. That's really the only one that comes out exact there with natural log. So we're not too far away from that. 1.01 versus 0.1. Subtract those two. And you're only 0.04 away. So the closer you are, the better your approximation is going to be. This is your delta x. And your x is always the one that works out exactly. So that's like those first three problems where they gave me an x and a delta x. So let's say I had, oops, I didn't want to write that, but I'll squeeze it in here. Y equals ln of x. That's the format I have, just like the last two were square root of x. So the format is natural log of x. The derivative of that with respect to x, remember for logs it's 1 over whatever you got. And then you multiply by a 1 over the ln of the base, which here is e. But that equals 1, so that goes away. And then you would multiply by the derivative of the domain part, but the derivative of x is 1. So the derivative of natural log of x, if you just have x, it's 1 over x. So then I can multiply both sides by dx and get this format. So now we're ready to plug in 1 there and 0.04 for this slot. And 1 over 1 is 1. 1 times 0.04 is 0.04. So if the x changes by 0.04, the y changes by the exact same amount, 0.04. The natural log of 1 is 0. So that I take that exact answer, and then you always either add or subtract this depending on which way you went. We went from a bigger number down to a smaller number. So that was like number 6, where I went from a bigger number down to a smaller number. So that's when you have to add the difference back in to get back up to the number you were at. And this is kind of a simpler case because the derivative was 1 over x and x was 1 and the answer was 0, so it doesn't seem to be changing much here, but 0.04, there's a lot of 0.04s here just because we're close to zeros and ones. So that's what we approximate this natural log of 1.04 to be. Our differential approximation is 0.04. What does the calculator say about that? So if I do 1.04 natural log of that just with a calculator, and they want 4 decimals, it's 0.0392. Pretty close. What's the absolute value of this difference? 0.04 minus 0.0392 is 0.0008. That's how much error you're having in this approximation. It's off by 0.0008. That's a pretty small difference. Tenths, hundreds, thousandths, 10,000. It's like saying you're off by 8/10,000th. So that's a very small error. So this one had a 0.0008 error. This one had no error at all. And this one was relatively large, 0.0116, but still 0.01 is 1 in 100. So it's like saying you're wrong 1 in 100 times, which is not terrible, but it's not as good as these other two. Okay, so demand for grass seed in thousands of pounds at price $P is given by this. So this is called the demand function, dP. P stands for price. That's in dollars. And demand is in thousands of pounds. Use the differential to approximate the changes in demand for the following changes in P. So if we go from 2 to 215, how much will the change in demand be based on a change in P from 2 to 215? It's about blank 1,000 pounds. Type an integer or a decimal. Okay, so here's the original function, the demand function, negative 3p to the third minus 2p squared plus 1458. So if I do the derivative of this, and think of this as the derivative of demand over the derivative of price. It's like dy over dx. So use your power rule here, negative 9 p to the second minus 4 p to the first, and then the derivative of a constant is nothing. Multiply both sides by dp for the change in price. And this is like getting that dy answer from before. So the price changed from $2 to $2.15. So this is delta P or dP. And you just subtract that. They used to just tell you what this is, but here you have to physically subtract it yourself. So the price is increased by 15 cents. That's how much it's changed. The price has changed. dP means how did the price change? There was a 15-cent increase in price recently, like with inflation. So that's what's going to go here. And then we started with $2 price. So that's our P. That's like the X in problems 1 through 3. So negative 9 times 2 squared minus 4 times 2 times 15 cents. So this is correlating very much like this right here, where we have an X exactly and we have a delta X that's a decimal, and you plug that in now after you've done the derivative. Okay, 2 squared's 4. 4 times negative 9 is negative 36. 4 times 2 is negative 8. That's negative 44 times 0.15. So the demand, see, this is like the law of supply and demand. When demand goes down, price goes up, and vice versa. Price goes down, demand goes up. So the fact that the price is increasing is going to cause less demand. So that makes sense that this answer is negative 6.6. So the demand is going down by negative 6.6, which is in thousands of pounds. So negative 6,600 pounds, in other words, but they want it, the units are thousands, so you don't have to change your negative 6.6. Type an integer or a decimal, okay. So what if you had a bigger increase in price, like from $6 up to $6.23? This was a 15-cent increase. Now what if it was a 23-cent increase? But what if it did so from a higher price? Would that make, you would think a higher change in inflation would cause the demand to go down more. But if the price is higher, that might supersede that a little bit. Okay, so we're using the same exact function. We don't have to redo this work again, just like that other one when I had the square root twice. So we're still going to have this. It's just that our value is changing from 6 to 623. So 6 is what's going in for the P's. And then 6, not 623, you have to subtract that. The change in X, in other words, delta X, is 23 cents. The inflation just went up 23 cents for this product, whatever it is. So that would go there. So negative 9 times 6 squared minus 4 times 6 times 23 cents. 6 squared is 36 times negative 9, I think is negative 144. No, negative 324. So negative 324, good thing I checked it. Minus 24, 4 times 6 is 24. And that's negative 348 times 23 cents. $348 negative times 23 cents. So demand goes down $80, not $80, 80,000 pounds. 80,000 pounds because it's 80.04, and this is in thousands of pounds. So 8,004 pounds. So the bigger increase in price led to this being a lot bigger, and maybe the size of the money caused that too. Negative 80.04. So this is what's happening in the country lately, where inflation goes up, causing prices to increase, and then demand goes down. And it can be a bad cycle sometimes, but that's why the government tries to do things to prevent it from getting worse than it could be, instead of just spiraling out of control. Okay, maybe let's do one more of these word problems. There was a good one. Square piece of metal. Circular. Okay, why don't we try this one? The shape of a colony of bacteria on a petri dish is circular, so we can think about the formulas for circles. Find the approximate increase in its area if its radius is increasing from 30 millimeters to 39 millimeters. Okay, so we have, let's talk about area of a circle, number 10. Area of a circle in geometry is pi r squared. Pi is just a constant, 3.14159. So area and r, those are the two variables here. So I'm really doing, for the derivative, I'm doing the derivative of area with respect to the radius. And this is just, pi is just a number, so 2 times pi, literally the power rule, 2 times pi, r to the first. That's the derivative. Multiply both sides by dr. So then this is what this whole section's about, is getting this kind of an equation where you're working with the changing of one variable. How does that relate to the change of the other variable? If I increase or decrease the radius by a little, what happens to how the area is changing at that moment in time? And we're increasing from 30 millimeters, so that's always the main variable, and we're increasing to 39 millimeters. So the difference of those two, that's the delta r, or in this case dr, when you do 39 minus 30. So the radius is changing by 9 units, 9 millimeters. At that moment in time, what's happening to the area? So 2 pi times 30 times 9. 2 times 30 is 60. 60 times 9 is 540. And I think they want pi left in the answer, so you just leave that there, 540 pi. So that's how much the area is going up. Since you square the radius to get area, a small change in radius can make the area go way up. And if we're doing 30 to 39, even though millimeters are small, this is just square millimeters. The area is square millimeters but because you're squaring a number, that's what makes it grow fast. Type an exact answer in terms of pi, so they definitely want pi left in there. The estimated change in area would be 540 pi square millimeters. And they put the square millimeters here already. And then for pi, they have a button on the toolbar down here, pi. So if they said type, see this says type an exact answer in terms of pi. So that's when you just leave pi in your answer, kind of like in trigonometry. But if they said round to the nearest 10th or 100th, then I would plug 3.14159 in for pi. Or some calculators have a pi button and you would actually hit that and get a better approximation of pi. If you just do 3.14 in cases like that, that's sometimes not enough to estimate it well. But don't plug 3.14 or even 3.14159 in if they say give me an exact answer. That always means leave pi in the answer. Okay, so we've seen a bunch of these, and again, I'll let you try some of these other ones. If you get stuck, let me know. But let's at least cover the next section's more important probably because it's the start of the next big concept in calculus. We've already covered two of the major three concepts in calculus. Limits was at the beginning of the course. Then we've spent a number of chapters working with derivatives and what we can do with them. Here comes the third major concept in section 7.1. Okay, well, let me skip this for a second. We'll come back to it. I want to just do an easier problem first, or a basic problem first. Here's a good one right here. So number 4, and before we do that, let me show you what this is coming from. So in a derivative, say your original function is 3x to the 4th minus 5x squared plus 6. The derivative, using the power rule, you do the exponent times the constant in front, and then you decrease the exponent by 1. And do that for each term. Exponent times constant, decrease the exponent by 1. And we know the derivative, that's nothing. So what this is called is, well, it has a couple of names, but what we're going to look at first is it's literally the antiderivative. You know how there's matter and there's antimatter that eliminate each other. Anti is the opposite. So there's an opposite process to a derivative, sometimes known as the antiderivative. It also has its own name that we'll see in a minute. But what if I started with, and they'll call this capital F to distinguish it from the little f of the derivative. What if I started with the answer to this problem? Is there a way I can backtrack to get what I know the answer should be, because it should be this? The question in the previous chapters is now the answer in this chapter. And the answer in previous chapters is now the question. It's like playing Jeopardy where you do it backwards. Well, because they're backwards and basically inverses of each other, you do the steps backwards and in reverse order. So there's two main steps here. You multiply the exponent to the constant. So instead of us multiplying, we're going to divide. And you decrease the exponent by 1. So we're going to increase by 1. And we're going to do it in the opposite order. In a derivative, you do the exponent times the constant first. That's going to be the last step this time. You decrease the exponent by 1 last. That's going to be the first step in reverse this time. So this, if this is f of x, the antiderivative would be little f of x. If the original is big F of x, the antiderivative is little f of x. which means I should get this answer down here. So you're actually going to increase the exponent by 1 first. You can rewrite the 12 here. Increase the exponent by 1 first, so that's backwards order and backwards step. And then you're going to divide by the exponent, but this new exponent that was created, instead of multiplying. And notice what that equals. 12 divided by 4 is 3, check, x to the 4th. So that's the power rule in reverse. You increase, you can write the 5 down, write the -5, write the base, you increase the exponent by 1, and then you divide by that new exponent. So you're doing the steps in reverse and in the opposite order too. If it can reduce, you would want to do, I was doing the wrong one, sorry. I was looking up there, but I was supposed to be up here. So it's right here, this 10x to the first. Increase that exponent by 1 to 2. You can have the -10 there. Increase the exponent by 1 and then divide by that same amount, that new exponent. And there it is, -10 divided by 2, that's -5. And there's the x squared. The only issue is, how am I going to get this 6 to happen? Because the derivative of 6 is nothing. So if I have nothing here, how do I get back to the 6 is the problem. And it turns out it's arbitrary. So we can just put plus a constant. We're never going to know that it was a 6 actually. So the convention is you just put plus c. There's possibly some kind of constant there. And because I won't know it going in this direction, it could literally be anything, and it could even be 0. There might not even be a constant, but 0 is a constant itself. It gets real easy for beginners to forget to put the plus c, and they count the whole answer wrong if you don't put that. You can do everything right, and if you don't put the plus c, the whole answer is wrong, unfortunately, in a homework problem like this. So here's section 7.1. I jumped to number 4 first to do a more complicated one. So, and this is the symbol to tell you to do the antiderivative, this little curly SE shape. So you go like this, and that tells somebody do the antiderivative. This is also called the integral. The integral or the antiderivative. Of 3x squared minus 5x plus 4. 3x squared minus 5x plus 4. And then maybe you notice there was a dx there, just like in section 6.6. So that's that little change in x. The little change in x, how's that going to affect the change in y? And it also represents the variable of interest, because later we'll mix variables in here too. And if it's dx, that tells you that x is the only one that matters. And you'll do your power rule, whatever rule you're doing for that variable. But if there was a 3x squared minus 5y, then the y acts like a constant actually. And you just treat it like any other constant. So that's also important to have this so you know which variable is the one of interest. Okay, so the antiderivative or the integral, you increase the exponent by 1 first, and then you divide by that new exponent. And sometimes these fractions reduce, sometimes they don't. This one does. So in a simplified format, I'll get x to the 3rd. Minus 5x, increase the exponent by 1 from 1 to 2, divide by that new exponent. Now this doesn't reduce. And remember, in derivatives, the derivative of a constant is nothing, but the derivative of a linear is a constant. So the antiderivative of a constant is linear. It's just going to turn into 4x. That's the shortcut. What's really happening is it's 4x to the 0. There's literally no x on that. So you're increasing the exponent by 1 from 0 to 1, and then you're dividing by that new exponent, but 4 divided by 1 is still 4. So you can think of it that way if you like, but a 4 constant turns into a 4x linear. And then the fact that if there is a constant in the function, if I take a derivative of it, it'll disappear up here in this antiderivative. So we always have to put a plus c because we don't know if there was a constant originally there or not. So here's the final answer. X cubed minus 5 halves x squared plus 4x plus c. Type an exact answer. Okay. X cubed minus 5 halves x squared plus 4x plus c. Okay, now let's go back to this. So this is also called an indefinite integral because you'll see what a definite integral is later. Indefinite integral, you automatically put the plus c at the end. So I want to do an indefinite integral or an antiderivative of 6x plus 2 dx. This one's easier, that's why I did the harder one first. 6x plus 2 and dx, x is the variable of interest. Okay, so you can write it down as it is and then increase the exponent by 1. It's currently a 1, so I'm going to increase it to a 2. Divide by that same amount. You can see the math isn't hard at all. It is, you got to get unused to the way you're used to doing derivatives. Everything's backwards here. Backwards steps and backwards order. The constant turns into a linear, and then we put plus c. And one thing I wanted to say on that last problem too, so this answer is 3x squared plus 2x plus c, since I can do 6 divided by 2. And I'll do it here too. What I was going to say on the last problem is, the one nice thing is when you get an answer, you can always check it, at least on the simple problems. What if I do a derivative of this answer? The derivative of this answer should equal the antiderivative of that problem. And the power rule would be 2 times 3, 6. X to the 2 minus 1 is 1. The derivative of 2x in derivatives is 2. And the derivative of a constant is nothing, which is why I need that there because I don't know what it would have been. Same thing here. If I take the derivative of this, x to the third is 3x squared. The derivative of this, you would do 2 times 5 halves, and the 2's would cancel. So yeah, negative 5x to the first, The derivative of 4x is 4, and the derivative of a constant is nothing. So you can check your answers, and you'll know that you did it right, as long as you remember the plus c. 3x squared plus 2x plus c. What if I forget to put the plus c? See? And they don't even tell you what's wrong. It just says it's incorrect. Apply the constant multiple rule and the sum rule. In other words, the power rule and the sum rule just means I have more than one term. That's not what's wrong with it. What's wrong with it is I forgot the plus c. And they don't even tell you that here, so you would be wondering, oh, what did I do wrong? But it's really easy to forget the plus c until you get used to that. And then they count the whole thing wrong, even though you did all the rule right, and you got the first 2 terms right, and you forgot one little minor detail. You probably, if this was a 6-point problem, you deserve 5 of the 6 points, but they give you none of the 6 points. So you just got to practice that till you get used to it so you don't forget that on a test. Okay, so the derivative of the antiderivative of a constant is going to take you back to the linear version, 9x, and then plus c. So that's a real easy one. And the derivative of 9x is 9. The derivative of c is nothing, so yeah, that double checks. So that's why I skipped these two originally, because I wanted to show you a better example first, so then you'd find these easier. Okay, explain what is wrong with the following use of the power rule. Okay, so they're increasing the exponent by 1 and dividing by that exponent, but the problem with that is that that's not actually x squared there. 5 over x squared is not x squared. That's actually 5x to the negative 2. You should always write things like this first, or like radicals, make them fractional exponents. So then you would do 5x, increase the exponent by 1, which would make it negative 1, and divide by that exponent. See, they're doing the wrong increase. They're increasing from 2 to 3, but you should actually be increasing from negative 2 to negative 1. And they divided by 3 when you should be dividing by negative 1. So it completely makes the answer wrong if you tried to do it directly like this. So the power rule is applied to the denominator rather than the entire integrand. Yeah, that's the mistake right there. You don't just do it to the derivative, or the denominator, I mean. You have to put it in its proper form first. So you're really doing power rule, so you want to have a power. You want to have a constant times a base with an exponent before you try to apply this rule. So that would be easy to fall for. You just add the you're doing the rule correctly, but you're only doing it on the denominator. Add 1 to the exponent and divide by that new exponent. Okay, so fractional exponents, here's a nice trick on these. So I want to do an indefinite integral of 11x to the 4/3 minus 13x to the 3/5 dx. It's exactly the same rule, it's just a little trickier with exponents that are fractions. So rewrite the constant in the base and then increase the exponent by 1. Now 4/3 plus 1. 1 can be anything divided by itself. So what you want it to be is 3 divided by 3, so that it has a matching exponent or denominator to this 4/3. So increasing 4/3 by 1 turns it into 7/3. And then you're dividing by that new exponent. And I'm going to show you a trick in a second. So then 13x, increase 3/5 by 1, and change the 1 to be this over itself, 5/5. Whatever the other denominator is, that's what you put over itself. So increasing it by 1 makes it 8/5. And then divide by that new exponent. And then hopefully don't forget the plus c. So if you're dividing by a fraction, that's the same as multiplying by the reciprocal. So you can flip, remember when dividing fractions, don't be shy, flip the second and multiply. You flip 7/3 to 3/7 and then you multiply it to the rest. Flip 8/5 to 5/8 and multiply it to the rest. And then it's just going to matter whether the fraction times the number reduces in any way. 11 and 3, neither one of those reduce into 7. 5 and 13 don't reduce into 8. So then you just multiply straight across. 3 times 11 is 33 over 7, x to the 7/3. Minus 13 times 5 is 65 over 8, x to the 8/5 plus c. They always like these fractions combined in nicer ways, and you don't want to leave them this messy. So 33 over 7, x to the 7/3 That was the first term. And then minus 65 over 8 x to the 8/5 plus c. And make sure you come all the way down before you put the plus c. Don't put it up in the exponent. I had to hit the right arrow a couple of times to bring it down. Okay, this is problem number 1 that was tricky. Don't try to increase that denominator exponent by 1. Common mistake. 12 over x to the 3rd dx. There's actually a rule later for if I get functions of x in the top and the bottom, then I'm not going to be able to do this. But because the top's just a constant, then I can write this 12x to the negative 3. Okay, now I'm ready to do the antiderivative or the indefinite integral. So 12x, increase the exponent by 1, negative 3 plus 1 is negative 2. Divide by that new exponent. It's the only term, so plus c. We can actually do 12 divided by negative 2. That's negative 6. X to the negative 2 plus c. They should take this answer. Here's another case where there's multiple ways to write an answer, and they should take any of them. Because you brought the x to the 3rd up to the top and made it x to the negative 3, one kind of convention is always put your final answer back the way the original problem looked. You don't have to, but that's kind of an unwritten rule there. So I could put that x to the negative 2 back in the denominator, and then it would be x to the positive 2. And these two answers are equivalent to each other. So they should take either one. Don't put the negative 6 in the denominator. I've seen people do that before too. And it's only negative exponents that move to the other half of the fraction. Negative numbers don't. Negative exponents have nothing to do with negative numbers. So they just say type an exact answer. They don't specify which one they want. And even back in the day when we used to do problems out of a textbook and you'd look up the answers in the back of the book when you're doing homework, they would sometimes have one version in the answers to the odd problems, and a student might have the other version, and they might think they were doing something wrong, but it's just an algebra issue of these two things are equivalent to each other. And even though in algebra they frown upon negative exponents in answers, then not so much in calculus actually. So negative exponents usually are not bad unless they specifically say don't give me one. So I should be able to put negative 6 x to the negative 2 plus c. And see, it doesn't bother them. But you certainly could have done negative 6 over x squared. There's nothing wrong with that either. That's actually preferred in algebra. But in calculus, it's not a big deal. Okay, so later we'll learn how to do this as is, even though it's messier. So actually here we get a little lucky that we can still manipulate this a little bit. But the ones later are, you can't really do anything to the problem at the start. But because we have a single denominator, we can. 1 plus 10 to the 3rd over 3t. If the denominator has more than one term, then you can't do what I'm about to do. But with one term, you can do this because it's the opposite of what the rule of common denominators is. I can rewrite the problem as 1 over 3t plus 10t to the 3rd over 3t. Normally you have this and you say, okay, I have a common denominator. I'm going to add them. We add the top and we put it over all over one common denominator. So going this way is the opposite of common denominators. But the reason I want to do that is because then I can have 1/3 t to the negative 1 plus, this would be 10/3, and t to the, that was a 3, doesn't look like 1 now, but 3 and 1, that's when you divide powers, you subtract exponents. And then there should be a dt at the end of this. See how there's a dt at the end? And I knew that because all the variables here were t, although that's not necessarily has to be the case. Just because you have t's in your problem doesn't mean this has to be dt, but usually if you only have t's, then they're going to put a dt there. But that means t is the variable of interest, not x, not y, not any other variable. And if there was a mixture of variables, that would make a lot more importance to it. But so some students, again, kind of zone out on this part just because it doesn't seem like you're doing anything with that. But that is to let you know, mostly let you know what the variable of interest is. Now, it turns out the second half of this is easier. I have my constant, my base, I increase the exponent by 1, and I divide by that same amount. And then you can think of this as 3 over 1. So then I can flip it to 1 over 3 times 10 over 3. Remember that trick? If it's 3 over 1 at the bottom, it's 1 over 3 in the top. So we're going to end up with 10 over 9 for this part of the answer. Now, here's a rule that you might not recognize right away, but watch this. What if I just tried to follow the normal rule here? 1/3 t, increase the exponent by 1. -1 plus 1 is 0. And divide by that new exponent. Dividing by 0 is undefined. And this answer is not undefined. What's happening is this power rule is not working because there's a special rule for this one. It's actually one we did earlier in the other section. So this can be a reminder to you. If you ever increase the exponent by 1 and divide by 0, there's a reason why that's not working out well. Because remember, natural log of t. If you had natural log of t in the previous chapters and you did the derivative of that, it's 1 over t. And then technically times the natural log of the base, but the base is e, so that goes away. So the derivative of a natural log of whatever it is 1 over that whatever it is. And that's what I basically had right here, especially if I ignore the constant part. So you might eventually reach a part where you know that 1 over t, oh yeah, that's the natural log. That's the natural log of t when I'm doing an antiderivative, because the derivative of natural log of t is 1 over t, so the antiderivative of 1 over t has to be natural log of t. And I can put a double 1 here, because 1 times 1 is 1. So this 1 over that's for the natural log, and then my constant's still 1/3. And it really needs to be 1/3 because the 3's in the bottom. I don't want to make that a 3 just because I thought that I used the 1 already. So this is 1/3 natural log of t. And then this will turn out to be 10/9. 10/9. Now, here's another rule from algebra. Remember that the domain of a log cannot be 0 or negative. So often what they do to avoid that, and let me see if sometimes they don't make a big deal about it, but they might count this wrong. Unless sometimes in the directions they'll say assume t is positive to get around that issue. But that could be an issue that what if t is negative, then I'm going to get an undefined log there. So plus 10 over 9 t to the 3rd power plus c. Whoops. T to the 3rd power plus c. Let's see if they say this is wrong, because we might need absolute value around that. Yeah. So it's all because this is another algebra issue, but you need that to be inside of an absolute value. So you're going to see this often on antiderivatives. If you do an antiderivative of 1 over a variable, it's going to be natural log, but you need to put absolute value there by technicality because the domain of a log is not allowed to be negative. See, that's all that was wrong with it. So it's easy to forget that on the middle of a test too. Okay, so now they're starting to hit us with problems. Number 7. I mentioned how we got lucky that this was a 3t right here. If this was 3t minus 5, then I couldn't do this. And there's another method for it that you'll learn later. Same thing here. If this exponent was higher than a 2, then there's another method for it. But because it's only a 2, here's what we could do instead. Although when it gets more complicated, you wouldn't want to do this. 9x plus 4 squared dx. X is the variable of interest. So because it's only squared, I could literally write it twice. Anything squared means that times itself. And then I could use FOIL to work it out. 9x times 9x is 81x squared. 9x times 4 is 36x. And you get another 36x right there. And then a 16. So 81x squared plus 72x plus 16. That's the same thing as this quantity squared. So now let me do the indefinite integral, the antiderivative of this. And now it's in a rule that you know actually. This is the first problem I did today, or not today, but in this section. This was the first problem I did. Problem number 4 was like this. So this is really the power rule of antiderivatives, or they call it the sum rule if you're doing more than one term, but I just think of the whole thing as a power rule. So do your increase your exponent by 1, and then divide by the new exponent. Increase the exponent by 1 and divide by the new exponent. And then remember that 16 becomes 16x. The constant turns into a linear. And then plus c. And 81 does divide by 3 27 times. 72 divides by 2 36 times. So we don't want to clean it up if we can. 27x to the third. Plus 36x squared. Plus 16x plus c. And I think they like a capital C. Let me see if I put a small c. Would they count that wrong? No, okay. It's typically a capital C, but apparently they'll take a little c too. So if you want to save a keystroke and not have to capitalize it, that's fine. Okay, so now we hit this stuff that we've seen a lot in other chapters as well. Find the equation of the curve whose tangent line has this slope. Remember tangent lines? We deal with that a lot. Given that the point -1, -8 is on the curve. Okay. So notice they put f prime of x. So that's a derivative. F prime of x is a derivative. 3x to the -6/7. So regular f of x, that's an antiderivative. I've gone from a derivative back to an original, that's an antiderivative. Undoing a derivative is an antiderivative. So do the rule here where you increase the exponent by 1. It's a little tricky. -6/7 plus 7/7. That's 1/7. Increase the exponent by 1 and divide by that new exponent. And if you're dividing by a fraction, you can flip it and multiply by the reciprocal. So that would be 21x to the 1/7 plus c. This is the original curve. The original curve would be 21x to the 1/7 plus some constant if the derivative was 3x to the negative 6/7. So I just went from derivative back to original instead of the other way around. From the original to the derivative, that's what we learned previously. Now, normally you put the plus c, but here we're not going to because we're told this right here. We're given a point on the curve. So then we can actually figure out what the c is. So x is -1 and y is -8. This is similar to algebra. You know how you find, they give you a line and they tell you find a line that's parallel to it that goes through some point. So you find the slope of the given line, and then parallel lines have the same slope. So then your answer is y equals that x plus b, but you don't know the b at that point. So then you have to temporarily plug in an x and a y that's given to you so that you can find b. It's a very similar deal here. I'm going to temporarily plug in -1 and 8 so I can find c. And I didn't do this on the first 8 problems because they didn't tell me a point that I had to work with. So remember, f of x is the same thing as y. This is equal to f of x. I'm back to the original f of x function. So -8 is f of x, or y, and -1 is x. So I can solve for the c now. If I have a 1 negative raised to the 1/7 exponent, that's -1. 1 to any power root is 1, and -1 to any power root, if it's an even power, then it's not going to come out at anything. It'll be undefined or imaginary. But if it's an odd power or odd root, then it's just -1. But if you didn't know that, you could do that in a calculator. So times 21 is -21. Oops. So -8 equals -21 plus c. Add 21. And you get 13. So in some cases, we can actually figure out what the constant is. And then there's also something called a definite integral where you can do it too. So I don't have to put the plus c now. I can get rid of this and put a 13 here. So I literally have an original function. The original function is 21x to the 1/7 plus 13. That's a normal graph or a normal curve or a normal function. It doesn't have a weird plus c in it. And then if I took the derivative of it, I would get this answer. The power rule part, you would do the exponent times the constant. You would get 21/7, which is 3. And then x to the 1/7 minus 1 would turn out to be -6/7. And the derivative of 13 would be nothing, so that's why you don't see anything in the derivative for that. But then I've done what they said. Find the equation of the curve whose tangent line has this slope at the given point. So it's 21x to the 1/7 plus 13. Whoops, see how I put that 13 accidentally in the exponent? That would be wrong. So you got to right arrow twice to get out of there, plus 13. The slope of the tangent line to the curve, okay. If the point 0.08, okay, fine. Yeah, same kind of problem. This is number 10. I'm given a derivative function, so that's a key that you need to do the antiderivative to go back to the original f of x. 7x squared plus 7x minus 7. And then I'm given the point 0.8, which is a y-intercept. Not that that matters here, but it turns out it's a y-intercept. So the original function is the antiderivative or the integral of the derivative function. and that would be the integral of 7x squared plus 7x minus 7 dx. So 7x, increase the exponent by 1 to 3, divide by that new exponent, plus 7x, increase the exponent by 1 from 1 to 2, divide by that new exponent. The antiderivative of negative 7 is negative 7x, and then plus c. There's no way to reduce or clean up anything here. So now we're going to, and this is going to be nice, we're going to put 8 in for f of x, and we're going to put 0 in for every x, which will knock them all away. So it's always nice when they give you 0 comma something for your point, because then the constant is literally the 8. That's the constant right there, since 0 is going to knock all these other x's away. So all I need to do is put a plus 8 here at the end, and then we have our original curve. So 7/3 x to the third plus 7/2 x squared minus 7x plus 8. Let me double check that's what I had. Yeah. Okay, here's a business problem. Find the cost function. Cost is c of x. Find the cost function if marginal cost is c prime of x and the fixed cost is $6. So that's a derivative. Marginal anything in business is derivative. That's the key word for derivative. Marginal cost function c prime of x. So that's just telling me I need to get c of x. I need to go from the derivative back to the original. C prime of x, that's marginal cost. How is cost change in any given moment in time? 12x minus 3. And then the regular function would be the integral or antiderivative of this. So I'm going to increase the exponent by 1 and divide by that new exponent. 3 turns into 3x plus c. And this could simplify to 6x squared minus 3x plus c. Here's the cost function, although I don't know the c, and they didn't tell me a coordinate. They told me that the fixed cost was $6. That's the x. So x is 6, but I don't know why. When we're doing the other way around in the previous chapter, they sometimes give you a coordinate, they sometimes give you an x. There you have, even if they only give you x, you could plug it into the original find y, but we can't plug it in the original because we don't know c either. If we plugged it into this, all that would tell me is what the slope is at that point. 72 minus 3 is 69. The derivative would be 69 when x is 6. Fixed cost is $6. Oh, maybe that's what that means. Okay, I think I understand now. So I don't think that's x actually. Fixed cost, that might be the constant. Maybe the constant is 6. Let's try that. 6x squared. 6x squared minus 3x plus 6, since the fixed cost. That's a constant. Yeah, okay. So yeah, otherwise there'd be no way to get that. You'd have two unknowns. Okay, so almost out of time here. We've got 4 of these left. Okay, that's a derivative, so you can take the antiderivative and get the original function. Same thing here. There's a derivative, and it's exponential. Go back to the original. Oh, this is good. We should definitely do this one. And then that's basically the same thing. Or okay. So definitely let's do this. This is a good application of this. So number 14, this is a physics idea. They give me a of t, that's the acceleration function. A is acceleration. 2t squared plus 9. So what you have is, in order, you have s of t. This is a position function. Where is an object at any moment in time? V of t is the derivative of s. And that's, in physics, that's velocity. How fast is the object moving? A of t, acceleration, this is the derivative of velocity, or the second derivative of position. So they gave me acceleration and they want velocity. So acceleration is 2t squared plus 9, and then I'm also told v0 equals 1. That'll get us the constant then. So to go from acceleration to velocity, that's an antiderivative because we normally go the other way as a derivative. So normally the derivative of velocity gets you to acceleration. So if you go from acceleration back to velocity, that's an antiderivative. So this, now you do this one's pretty easy to work with. So increase the exponent by 1 and divide by that new exponent. The antiderivative of 9 is 9t, linear, and then plus c. This is the velocity function. And then they told me velocity at time 0 equals 1. This is like f of x equals y in algebra. So that's telling me the t is 0 and the velocity itself is 1. So you put 1 in the y slot, 1, and you put 0 in for the t's, which knocks them all away. So the c is 1 then. It's always nice if they give you 0, 1. That's like giving you the coordinates 0, 1. So all the t's, once you put a 0 in for them, anything times 0, 0, and they're all going to go to 0. So the constant equals the y part of it, 1. So then I get a formula for velocity if I want to know how fast an object's moving. 2/3 t cubed plus 9t plus, instead of plus c, now I can put plus 1 since I was given a 1 exact coordinate. And then I've got a normal looking function that's all numbers. There's no funky plus c in there anymore. So 2/3 t cubed plus 9t plus 1. And then this one's even better, this number 15, because now they want you to go all the way back to s of t, the position function. And we're told velocity at 0 is -2, position at 0 is 4, and start with this function here, number 15. I'm starting with the acceleration function. (15/2 square root of t). And I'm going to go ahead and make that t to the 1/2. Square root of t is t to the 1/2. Plus 2e to the -t. That's the acceleration function. So the velocity function would be the antiderivative of this acceleration function. Okay, so increase the exponent by 1. t to the 1/2. If you increase 1/2 by 1, you'll get 3/2. Divide by that 3/2, which is the same thing as multiplying by 2/3 the reciprocal. And then you can get rid of that. Now, this is its own rule. Remember, on derivatives, if you had 2e to the negative t, the derivative of that, the derivative of any exponential is itself first, and then you multiply by by ln of the base, but ln of e is 1, and then you also multiply by the derivative of the exponent, and that would just be -1. So this would actually be times a -1, and it would be -2e to the negative t. So in the opposite process, the last thing we did there was we multiplied by the derivative of the exponent. So for us, we're going to divide by the derivative of the exponent first. The derivative of the exponent is -1, so we need to divide this by -1. And that's all that happened because the rest was itself. The derivative of 2e to the negative t was 2e to the negative t, and all I did was multiply by the derivative of the exponent. So here I just have to divide by the derivative of the exponent. So these 2's will cancel. 3 can go into 15 5 times. So my velocity function should be 5 t to the 3/2. And this can be -2 right there. -2e to the negative t plus c. So we need to find c next, and the reason we can do that is they told us that v of 0 is -2. So that's where you put the -2 here, and then you put zeros in for all the t's. Now normally that makes them disappear term by term, but it doesn't with e. This part goes to 0 because 0 to any power is 0 times 5 is 0. But e to the 0 is not 0. E to the 0 is 1 times -2 is -2. So then you would have -2 equals -2 plus c. And you could add 2, and c would be 0. So the constant can be 0. I even mentioned that earlier. So then there is no constant. There doesn't have to be a constant. We just don't know if it's 0 or something else. So that would leave us with this velocity function, 5t to the 3/2 minus 2e to the negative t. And now repeat the process one more time. Because we want to go now from velocity to position, which is another antiderivative. So do the antiderivative here, 5t, increase the exponent by 1, now you're going to be up to 5/2. Divide by that new exponent, and then you can flip it and do it to the top. And these 5's would cancel also. So 2t to the 5/2. We already did this. All that happens is you're going to constantly divide by -1 because the derivative or the antiderivative of e to the t, or even -t, is itself basically. So you basically get itself, but the derivative of the exponent is -1. That's what you divide by instead of multiplying by it. So this will turn back to +2 e to the negative t plus c. And now they tell me s of 0 is 4. So I can put the 4 here. The 0 right there is going to zero that part out. But the plus 2 e to the 0, that's not going to zero out. It'll just, this part will equal 1 times 2 is 2. So then you're actually going to get a constant. 4 equals 2 plus c minus 2. C equals 2. So the final answer for the position function is 2t to the 5/2 plus 2 e to the negative t plus 2. A lot of 2's in there. 2t to the 5/2. They could have put the velocity as like a part A answer and then done position as part B. And that way you could make sure you got the velocity correct before you moved on to the next one. 2t to the 5/2 plus 2e to the negative t. And then I got a constant of 2 out of that. Okay, so I actually did 13 of the 15 in this section, and we're over an hour and a half, so it's a good stopping point, and you got a good basis now for 6.6 and 7.1. We have one more video left this week. Tomorrow we'll be doing 7.2 and 7.3, which will be more with these antiderivatives.